All right, well, we're in the home stretch. 2 more weeks. We're almost there. So let's finish up our talk of Laplace transforms and using those to solve differential equations. And last time we got to the point where we were looking at unit step functions and seeing how we can use those to deal with piecewise defined functions. And what I want to do today is kind of wrap it all together by showing, all right, so here's how we'll take the Laplace transform of them, and then how we can do the inverse Laplace transform to find out what our functions look like. So I'm going to go to the board and just remind you how we can write these things being a piecewise defined function, as a function with the step function, and then we'll kind of go from there. So let me switch to the whiteboard view.
Yep. Oh, thank you for the burritos.
All right. So let's take a fairly simple piecewise function and talk about defining it as a using step functions. So let's just do this. Let's say we've got f of t equals, we'll give it 3 parts. Let's say that it's t, 2, and say 7 minus t. Let's go with this first one when it's less than 1. The second one will be when we're between 1 and 3. And then the other one's going to be from 3 on out. Okay, so let's kind of remind ourselves how this unit step function works. So the unit step function, u of t, it's the one that's 0 when t is less than 0, and it's 1 when t is greater than or equal to 0. So the best way to think about it is it's something that turns something on, right? It's off until we hit 0, and then it turns on. And so we can also shift these things so that we're not starting at 0, but we're starting anywhere. So all you have to do is do a t minus c. And basically that looks the same, except now where we're switching on is at t equals c. Okay, so that's all you got to do to shift it over. But I mentioned last time that what you're going to see me write is u sub c, because it's one less stroke. I don't have to write the minus sign. And me being lazy, well, that's what I'm going to do. Okay, so we're going to use this notation, but remember that's how we show that it gets shifted. Okay, so let's come back to this function, and let's talk about how we're going to write this in terms of the unit step function. So basically where you want to start is with the first rule. So the first rule says we've got t, so I'm going to go ahead and just start with t. Now, it gets interesting when we get to 1, because that's when things change. So what I'm going to do is I'm going to put a plus u sub 1. Okay, so we're going to turn on something at 1. So what we're going to multiply by then is what we turn on. So we need to turn on 2, because at this point now we're at 2. So we're going to put a 2. But the problem is if I leave it just like this, what I'm going to have is the original t plus 2. But I don't have t plus 2. I just have 2. So not only do I need to turn on the 2, I need to turn off the t. So I'm going to put minus t. So I literally think of this as a bunch of turning ons and turning offs. All right, so now when we go to 3, now we're going to want something turning on at 3. So the question is, what do we turn on? Well, we're going to turn on 7 minus t. But again, I have to turn off the 2. So I'm going to put minus 2. You'll notice that I didn't do anything with t. I didn't do anything with that first rule. because that first rule got turned off. It already got turned off, so it's not there anymore. So this piecewise defined function can be written in terms of the step function as t plus u1 of t times 2 minus t plus u3 of t times 5 minus t. Okay, so Monty, the 7 minus t minus 2, the 7 minus t was the rule that we were turning on. So that was that piece. Okay, cool. And then the 2 is what we were turning off. All right, so that's how we go about turning these into step functions. All right, so the whole point of this is to be able to do Laplace transforms. And what we saw last time is that if you do the Laplace transform of a unit step function that turns on at c, what we end up getting is e to the minus cs over s. So we basically just went to the derivation, right? We went to the definition of Laplace transforms, we applied it to the step function, and this is what we found. All right, so really what this is going to do for us is going to allow us to go backwards, right? We're going to be able to take something that looks like this and turn it back into the step function. But we should probably do one more thing, which is, what do we get if we do the Laplace transform of this step function times another function f, right? Like, how are these guys related so that we can literally go backwards? Okay, well, here's what I want you to see is, here's a theorem. So let's just go this way. Let's let big F of s be the Laplace transform of f of t. Okay, so whatever the function is we're dealing with, we take its Laplace transform, that's big F. Okay, so then what we know is that the Laplace transform of e to the ct times f of t, so we're off by e to the ct, this just equals f of s minus c. And I'll go ahead and show this to you. It's actually pretty easy. You just go back to definition of Laplace transform. So here's your proof. Okay, so we take the Laplace transform of that. That's going to be integral from 0 to infinity of e to the minus st times e to the ct f of t. Right? Definition of Laplace transform is take your function, the function's there, what's in the red, and multiply by e to the minus st and integrate. All right, well, if I use the rules of exponents on this, this becomes the integral from 0 to infinity of e to the minus s minus c times t times f of t. So when I multiply these together, I can add the exponents, and then I just factored out a minus t. Okay, well, if you look at this, and you just look at its form, you can see then that it's the Laplace transform, or sorry, it's equal to big F of s minus c. Because if you go back to the original definition of Laplace transform and you put in s minus c, right, look at this first line, you plug in s minus c, you get exactly this form. Okay, so what this tells us is that a horizontal shift, a shift in our Laplace transform, actually leads to an exponential multiplier on our original function. Okay. So basically, this is going to allow us to take things backwards. So let me show you an example. Okay, so let's say, are we good if I eliminate this proof? We got space, we got it all.
Yeah.
So here we go. Let's say that this is what we get from a Laplace transform. Okay, it's going to be 1 over s squared minus 4s plus 5.
Wow.
So what we saw is that to do these, we need to get them into one of the nice forms. And one of the nice forms, well, a lot of the nice forms, actually have an s squared in the bottom. So let's complete the square. Let's complete the square on the bottom there. So if we do that, this is the same as 1 over s minus 2 squared, right? The good old divide by 2 square business. And then plus 1. All right, now, we don't have any that look exactly like this, but we've got some that are close. So if you go back to your chart, right, your chart of all the exponential form or all the Laplace transform forms and all that good stuff, this looks like a 1 over s squared plus 1, which would be a sine of t. So we know that if we've got a function f of t equals sine of t, then we'll call it big F of s is 1 over s squared plus 1. So what we've got here in G is exactly this thing F just shifted by 2. Okay, well now this is where we're going to use the theorem we just proved. So that tells me that G of s is the Laplace transform of G of t equaling e to the 2t, because we're shifted by 2, so e to the 2t, times sine of t. All right, so if in the process of getting this stuff set up, we end up getting a form that looks a lot like one that we know, but there's some sort of shift, that just tells us throw in that e, whatever that shift is. Okay, so we got that. But there's one more thing I want to talk about, which is what do we get if we've got this e to the minus cs times some function, some Laplace transform we already know. All right, so here's the last one. Is what if we have, say, g of s equals e to the minus cs times f of s. So what kind of function is going to give us that? Now, the e to the minus cs should trigger in you, oh, that's going to be a step function. And then you probably also want to go with, well, it'll be whatever the function was that gives us s. And that is true, but it's not quite exactly that. What we know is that the inverse Laplace transform of this, so g of t, it's going to equal the step function that starts at c. That definitely comes from this. But it's not just f of t, it's actually f of t minus c. So it's not quite exactly what you think, but it's pretty close. So really what we're going to get is whatever that function was, also shifted to start at this point. Okay, now to prove this, it's actually pretty easy because you can again go to the Laplace transform definition. Like let's take the Laplace transform of g of t. Well, that's going to be the integral from 0 to infinity of e to the minus st times uc times f of t minus c. Now, because we're starting at c, right, this thing turns on at c, it's 0 otherwise. That turns this into an integral from c to infinity, e to the minus st times f of t minus c. And if we want to relate it back to an actual Laplace transform, we want to shift this. We want to shift it so that it starts back at 0. So that means I need to add c to all of the t's, right? And so this is going to give us then e to the minus s times t plus c times f of t plus c minus c. And then again, by rules of exponents, I get an e to the minus st minus sc. That can come out front as a multiple. So I get e to the minus cs times the integral from 0 to infinity of e to the minus st f of t. And notice that this piece right here, that is the Laplace transform of f. And so we've got our proof. That's e to the minus sc times f. Now, in reality, it's not very often that we're finding the Laplace transform of this kind of function, where it's a step function times that function that's been shifted. But it is very often that we want to go backwards, that we end up with something like this, and we want to figure out what function gave it to us. All right, but now that we've got it, we can just do those inverse Laplace transforms and everything is good. So let's do a couple of examples, and we'll start easy and then we'll make it more complicated. All right, so here's an example. So let's say we've got some Laplace transform that looks like e to the minus 3s times s over s squared minus 1. So here's how you want to approach this. You want to kind of separate it out. So we've got an e to the minus 3s. So that e to the minus 3s, that immediately tells me that there's going to be a u sub 3. So that's what this piece tells me. So now what I need to do is actually look at the s over s squared minus 1 and figure out what kind of function gives me that. All right, so anyone recognize that one?
I can't fully see under the line.
It's s
Oh,
squared
yeah.
minus 1.
Yeah.
So you can look at your chart. Again, I did post one of them on Canvas. It's in the files in our class if you want to look at it. And I guess Thea also put one up. Pretty sure this is one that we did in class, actually.
It's the hyperbolic sine.
Okay, so we know that this one is hyperbolic, except it's not the hyperbolic sine. It's the hyperbolic cosine because of the
I didn't
S.
see the S. Got
Are
it.
you guys getting
Yeah.
bad glare, or I can try to. If I make it more vertical, does that help?
Yeah, that's
I spaced out. It wasn't anything to do with the board.
Okay. Well, again, maybe this will help a little bit. All right, well, we know that S over S squared minus 1 is a cosh. It's a cosh of t. Okay, so we know that if we've got f of s equals s over s squared minus 1, this tells us that f of t is cosh of t. So we know that that piece is going to give us a cosh, but it's not going to be cosh of t. It's going to be cosh of what? We just saw that theorem that we proved just a minute ago, that it's actually f of t minus c. So this is going to be cosh of t minus 3. And so that's what the second piece gives us. So we'll just take whatever it is, but make sure that we shift it over. All right, well, here's another one. Now, this one came from an example we did last time. I don't remember how it started, but I know that we were solving for a Laplace transform. It's the one that I wrote at the bottom of the board, for those of you who were here last time and remember when I was talking about how I could write all those snarky things about Wes and stuff down there. But we had gone through one of these and found this Laplace transform for the function y. But now we're ready to actually go backwards and figure out what y equals. So let's see if we can do that. Let's go backwards here. So we'll start with 1 over s. So that one, if you look at your chart, or you might have this one memorized because it's a pretty common one.
Yeah, it's just one.
That's just 1. Okay, so that's just the function 1. Now, the other part, you notice that there's an e to the minus s. So that e to the minus s tells me I need a step function. Where do I need that step function to turn on? What's c? Well, remember, c is what we're multiplying to that s. So in this case, we're multiplying by 1. So we're going to have a function that turns on at 1. So that e to the minus s tells me I'm going to turn something on at 1. Now, what I turn on at 1 Depends on what this is. So let's do that below here. Let's take this 2s plus 2 over s cubed and see if we can figure out what function gives us that as a Laplace transform. So I'm going to help us out by first separating it into a 2s squared and a 2s cubed. So now we can look at our chart again, and we see that there are a set that have s to a power below them. Like if you look at it, you'll see it's an n factorial over s to the n plus 1. So that's where we are. So let's see what these are going to give us. So for s squared, that's going to be t to the first, because t to the first gives us just 1 over s squared. So can you guys still hear me?
Yeah, I can hear you fine.
Yep.
Okay. Because I just lost my sound for a second. Oh, great. My computer just told me the internet connection is unstable. So if, let's just get this out there, if for any reason it gets like funky and frozen, or I just blink out of appearance, that'll be because there's a technical issue. I'll do my best to get it resolved, but if like I go away and I don't come back in the next 5-6 minutes, feel free to go, because it could be a bigger issue. Anyway. Okay, so let's come back to this. So the 2 over s squared, that's going to come from a t. T to the first is going to be 1 over s squared. So this would suggest 2t. The 2 over s cubed, well, that's going to be from a t squared. And t squared, we see that that's equal to 2 factorial over s cubed, which is exactly that. So this Laplace transform comes from the function 2t plus t squared. Okay, but that's not what I'm going to put up here, because I have to shift it. I have to shift it by 1. So I'm going to get 2 times t minus 1 plus t minus 1 squared. So literally the hardest part of this is remembering to put in your shift. It's, you want to go through the process, you want to find what that function is, but then you have to remember that you have to shift it over however far the E is telling you. All right. So give me 1 second here, guys.
Okay.
My phone keeps buzzing at me. I'm going to tell it to shut up. All right. Okay, so this is the nuts and bolts of how we deal with the step functions. So let's actually go through a problem where we've got a piecewise defined forcing function, and we'll find our solution by way of using Laplace transforms, and we'll talk about what our other option would have been otherwise. So I think I'm going to give you 2 of these. We'll go through 2 of these because that should be plenty for you to see the process, but not so much that you just get tired of it and don't care about them anymore. All right, so let's go with this one first. Let's say that we've got the differential equation y double prime plus 4y equals, And I'm just going to call it g of t. I'll tell you what g of t there is in a second. But we're also going to make it an initial value problem. So let's just say we've got y of 0 is 0, and y prime of 0 is equal to 0. But this is g. G is going to be a piecewise defined function. It's going to be 0, t minus 5 over 5, and then 1. And it's 0 whenever we're less than 5. It's t minus 5 over 5 when we're between 5 and 10. And then it's 1 as soon as we reach 10. So if you wanted to think of this as some sort of an applied problem, we could make it a spring kind of deal, right? Because this is definitely format for a spring. There'd be no dampening, but there would be a forcing function. So for a while, it's just stationary. Nothing's forcing it. But then we start applying a force. And for 5 seconds, we're applying a force that looks like this. It basically goes from 0 up to 1. So it's a nice constant. We start applying more force, more force, more force. And then once we get to 10 seconds, we keep that same force applying. Right. So that's what's going on in this situation. But we're going to go ahead and solve this thing using Laplace transforms. So first things first, let's write this out. Let's write this g using the step function, unit step function. All right, so here's what this is going to look like. We start with 0. So I'm not going to do anything with the 0 right now. But at 5, I have to turn on a function. So I'm going to write here u sub 5 of t. And what we're going to turn on is t minus 5 over 5. Then we need to turn something else on at 10. So I'll put u sub 10. And what we're going to turn on is 1. But now we also have to turn off the t minus 5 over 5. So I'll put that as a subtraction. So I'm going to simplify this a little bit. I can pull that 5 out. I just want to get it as a constant multiple. So it's going to be 1/5 times u sub 5 times t minus 5. And then we're going to get minus u sub 10. So if I get a common denominator and then I factor out that minus sign, you'll see why I do that. That turns to just u sub 10 of t times t minus 10. All right, so far so good. So now we want to do the Laplace transforms. So we're going to take a Laplace transform of each side of this differential equation. So I'm going to erase g in the piecewise form, because really what's important is this step function form. But I know you already have it written down anyway. So let me just go ahead and erase this so we can make some space for our Laplace transforms. Okay, so we're just going to take a Laplace transform of each side. All right, so let's start with y double prime. So we saw that there is a formula for higher derivatives. There's a nice little pattern for the Laplace transform. But what this is going to give us is s squared And this is one that I know is on the chart that I supplied you. I don't know if it's on the one that Thea posted in your board. But for the derivative, so it's going to be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 . So that's that Laplace transform. The 4 times Laplace transform of y, of course, is a 4 Laplace transforms of y. And then that's going to equal the Laplace transform of this thing. All right. Well, we've got a 1/5. So that 1/5 just stays as a 1/5. It's a multiple. So then we're going to do the Laplace transform of u sub 5 times t minus 5. All right, now this one is shifted perfectly, right? We just saw that this is going to equal e to the minus 5s. And I apologize that this has a 5 in it, but because my 5s and s's look the same. That's going to be e to the minus 5s times the Laplace transform for just t. And we saw that t is 1 over s. Okay, I'm going to be like really careful about making those 5s look like 5s. Okay, now when we go to the u sub 10, same deal. We're going to get minus e to the 10s, sorry, minus 10s. And then t minus 10, that's just the function t that's been shifted over 10. So we're going to get exactly the same thing, which is a 1 over s. So there's the Laplace transform for that piecewise function. All right. So now let's evaluate these guys. Let's actually plug in our values and see what we get. So the y of 0, the y prime of 0, those are both 0. So those are going to go away. Oh, I just realized I did something wrong. These are supposed to be squares. Laplace transform of t is 1 over s squared. 1 over s is the Laplace transform of 1. Apologize. All right, so those go to 0. We have an s squared plus 4 that we can factor out of that Laplace transform. So we get L of y is equal to, we're going to get e to the minus 5s minus e to the minus 10s. I'm going to factor out that s squared. So on the bottom we get 5s squared times s squared plus 4. All right. So at this point, we know what the Laplace transform of our solution looks like. And now we want to figure out what is that function? What does this thing actually look like? All right, well, let's not worry about the bits with the exponentials. Let's concentrate on the other part. I'll even factor the 5 out, so we don't even really have to worry about it. But we want to look at this. What kind of function is going to give us 1 over s squared times s squared plus 4? So we need to break that up using partial fractions. So this is going to be a over s plus b over s squared plus cs plus d over s squared plus 4. So I just want to remind you, when you have a repeated factor, like this guy s squared, you need to have 2 possible fractions, the one over s and then the other over s squared. Now, because I know nobody really cares at this point about doing the actual steps there, I'm just going to jump to what that equals. So 1 over s squared times s squared plus 4, it actually breaks down into 1/4 times 1 over s squared plus minus 1/4 times 1 over s squared plus 4. So there was some work involved there, but I'm going to skip over it. Okay, so let's think about what this function is going to look like. So the 1/4, this is 1/4, but the 1 over s squared, that's a t. The next one, the 1/4, again, is a 1/4. But 1 over s squared plus 4, so that looks like the form a over s squared plus a squared, where a would equal 2. But that would require a 2 on top. So let's go ahead and put that in. So if we were to put that in, we'd have to multiply a 2 on top and bottom. So the 2 on the bottom is actually going to give us a 1/8. And then 2 over s squared plus 4 is sine of 2t. All right, so that's the bit that comes from the s squared times s squared plus 4. So I think we're ready to get our y. So here's how this is going to break down. Y is going to equal 1/5, is that 5? Let's pull that out. We're going to have a piece that starts at t equals 5. So there's going to be u sub 5, and that's going to be multiplied by this function shifted. So we're going to get 1/4 times t minus 5 minus 1/8 times the sine of 2 times t minus 5. So that's the bit that involves the e to the minus 5s. So basically what happens is nothing's going on, but then at time 5, this function turns on. All right, and then we go for a while until we get to the 10. So now we're going to have a minus. The 10 tells us to make a u sub 10. But then the function that's turning on is the same as the one we saw before, except shifted to start at 10. Whew. So that one's so long that I can't even write it on the width of this whiteboard. But there's that function. It is a piecewise function. And we could even write it as a piecewise function if we want. Right? It's 0 until we hit 5. At 5, it's going to be 1/5 times this stuff. And then at 10, it's going to be 1/5 times the difference of these two. But we'll go ahead and leave it like this. Ugh. All right, so I know exactly what you're thinking. And yes, this is a pain. There's a lot of stuff we have to pay attention to. But remember the whole point is that this is now just algebra. We haven't done any calculus in here. Like, did you notice that? Not a single step of what we did was calculus. So if you think historically, because calculus was a little bit rougher, this is kind of nice. Laplace transforms, we did the calculus once. We did it once to get the forms for all the different functions and their Laplace transforms. But once we have that, we can take any differential equation and turn it into an algebraic equation. Which, I mean, yeah, algebra is algebra, but it's at least doable, where sometimes this calculus isn't. And I promise you, this is actually faster than if we had tried to do it with various initial conditions as things turned on and off. All right, well, this also shows you why I'm only going to do 2 of them, because after this one, I know that you guys are already like, yeah, don't care anymore. So let's do one more. Let's practice one more here and see what this one looks like. All right, so let's go with this differential equation. Let's go with 2y double prime plus y prime plus 2y. And again, that's going to equal a piecewise defined function that I'll tell you in a second. But we'll also go with the same initial conditions as before, that both of these things starting at 0 are 0. But this time, let's make g of t be this. It's going to be 0 when t is less than 5. It's going to be 1 when t is between 5 and 10. Now let's go 20. We already did a 10. Let's do a 20. And then it's going to be 0 when it goes back to 20. So in a real situation, this would be, again, let's say we've got a spring, because this could be a spring thing where there is a dampening force. But basically, we're leaving it alone. We apply a force. Right? We apply a force for 15 seconds, and then we stop, and we remove that force. So this would be a force turns on and then off again. Okay, so there's G. So just like last time, let's start by writing G as a Laplace, or as a step function kind of deal. So if you think about how this works, G of t, the first thing that turns on at 5. So we're going to get u sub 5. And what turns on is 1. We turned on the function 1. Okay, And then we don't do anything for a while till we get to u sub 20. And now we want to turn on 0, and we want to turn off 1. Now, if I'm doing this myself, I don't write it as 0 minus 1. I just go to minus 1 because I know I'm turning it off. But I want to remind you what we're doing is we're building these as turn on with the plus, turn off with subtraction. All right, so this actually then is just u5 minus u20. All right, well, now we're ready for our Laplace transform. So let's take a Laplace transform of each side. So on the left, we need 2 times the Laplace transform of y squared, or sorry, y double prime. So that's going to give us s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. So that's this. We then need to add to that the Laplace transform of y. Well, y prime. The Laplace transform of that is s times the Laplace transform of y minus y of 0. And then we're going to add to that the Laplace transform of 2y, which is 2 times the Laplace transform of y. So that's what's on the left. And then that's going to equal the Laplace transform of this step function right here, the u5 minus u20. So that's going to be e to the minus 5t times the Laplace transform of 1, which is 1 over s. And then we're going to have minus e to the minus 20t, also times 1 over s. So that's the Laplace transform of this series of step functions. All right, so now let's plug in our initial conditions. We have y of 0, 0, and y prime of 0, 0. All right, that's what we started with. So all of these things go away. By the way, you're going to really like it when your initial conditions are equal to 0, because lots of stuff goes away. All right, so that's going to give us the Laplace transform times y times, if we just look at what's left, I can factor it all out. I get 2s squared plus s plus 2. And that's going to equal 1 over s times e to the minus 5t minus e to the minus 20t. I just factored out the 1 over s. So the Laplace transform then, if I just divide by that factor, that's equal to 1 over s times 2s squared plus s plus 2 times this e to the minus 5t minus e to the minus 20t. All right, so now comes partial fractions. So let's again just look at this guy right here. Let's not worry about the e bits because we know what that's going to do. So instead, let's look at the 1 over s times 2s squared plus s plus 2. This one, if we do partial fractions, we're just going to need the 2 pieces. So there's going to be an a over s and then a linear unknown, so the bs plus c on top of that 2s squared plus s plus 2. All right, well, again, because I know you don't really care, let me just jump to what this looks like. So if you solve this, you get a equals 1/2, b equals -1, and c equals -1/2. So that means that this thing will split apart then as 1/2 times 1 over s. And then we're going to get minus, that's going to be s plus 1/2 over 2s squared plus s plus 2. All right, so now we got to go backwards. We have to figure out what functions give us these. Now, the first one's pretty easy. 1/2 times 1 over s, that's just going to be 1/2. So the function that we're going to have to shift just has a 1/2. But this other one, we definitely need to do some algebra on it. So you're going to want to complete the square. Okay, well, maybe you don't want to complete the square, but we're going to have to complete the square on this. So to complete the square on that, you have to factor out a 2, because you need to leave with just an s squared. So you factor out that 2. I would actually factor out the 2 on top as well. So you've got a 4 out front. And then do your steps. I'm just going to jump to what that looks like. So again, we've got the 1/2 times 1 over s. And then the other one is going to look like minus 1/2 times, on the top, you're going to get s plus 1/4. No, let's just do this. It's going to be s plus 1/2. And then on the bottom, we're going to get s plus 1/4, that quantity squared, plus 15/16. So really just be glad that I'm doing this for you. And so now what we need to do is go and look and see if we can find a form that matches this. So again, I don't know what chart you're looking at. If you look at the one that I gave you, if you look down and you look at the exponential times sine and cosine, that's what we've got here. Because this s plus 1/2, we could actually write this as s plus 1/4 plus 1/4, which means we can actually break that into 2 different pieces. So one of them is s plus 1/4 over s plus 1/4 squared plus 15/16. And the other one is just 1/4 over s plus 1/4 squared plus 15/16. And each of those give us different forms. So this first one is going to give us an exponential times a cosine. The second one is going to give us an exponential times a sine. So what this is going to look like then, when everything is said and done, let me erase this piece. So what I'm going to write here isn't the solution to this yet. It's what we would have to shift. So the f of t, the thing we have to shift, there was already the 1/2. Remember there was the 1 over 2s. or 1/2 times 1 over s. That was the 1/2. But then what we're going to get is a minus 1/2, because that was out in front of all of this stuff. This piece right here is going to give us e to the minus 1/4 t. That's what the s plus 1/4 does. And then we get the cosine of the square root of 15 over 4 times t. And that's what the 15/6 does. So that was this piece. And then the other piece, go ahead and continue it over here, plus, space. So again, this is going to give us an e to the minus 1/4 t. There's going to be a sine of root 15 over 4t. But we also need a multiplier on this. We need a 1 over root 15. And that's needed because the top doesn't quite match as the square root of that. We're off by a square root of 15. But this is the inverse Laplace transform of the bit that's there in the red. But we're still not done. Because now what we need to do is we need to shift those so that they match these two. So the first one is going to be u sub 5 times all of this, where we plug in t minus 5. The second piece that we're subtracting is going to be a u sub 20. And again, we need to shift all of these off by 20. So we put in a t minus 20. So I think what I'm going to do, let me see if I can do this. I'm going to write it on the side, and then I'm going to turn it sideways, because I might actually have enough space if I do it this way. So I'm going to take out my earphones. So if you say something, I can't hear you. So just hold on a second. Or this is when you can talk to each other and make fun of me. Feel free.
Ooh, we're getting fancy here.
Dude, this is some 4D chess that's going on, man.
Yeah, it's dope.
Oh, good lord.
Wait, who's calling?
All right, so check out this beauty. So here it is all written out. So first, I factored out the 1/2. There was a 1/2 everywhere, so I just pulled it all the way out. Okay, but then we have u sub 5 times that remaining function. So it was the 1 minus, because I factored out the 1/2. And then all this other stuff, notice where I put a t minus 5 in for all those places where there was a t. Then I subtracted u sub 20, because we're turning this off at 20. And it's that same function, but again, everywhere instead of a t, I put in a t minus 20. So I heard somebody chuckle, I don't know who it was, and Money just put in the chat, yikes. Oh, no doubt. No doubt. These things are big and gnarly. But think like a mathematician. Mathematicians, we love it when we can do something. And we can do it. We can actually take care of these piecewise defined functions now using only algebra.
Never tell a mathematician you can't. Otherwise,
Oh, yeah.
they'll find out some way that you can.
That's the fastest way.
It's not going to be the most elegant way, but hey.
True. True. And that's the fastest way to get something invented that you may not, that you might regret later, right? It's like, okay, I'll come up with something and I'll make it work. Oh, and I just realized you actually can't even see the whole thing. There you go. Now you can
Oh,
see
God.
the whole. So, you know what, Will, and I just called you Will, sorry, Wes. I can too integrate u to the x squared. I'll just give you the power series for it. So, no worries. Anyway, okay, so I want you to realize a couple things about this. Let me turn the screen so that viewers who come later don't have to look at that nonsense for longer. They can look at me instead. Okay, so a couple of things here. So first of all, realize that you're going to be able to do any of these. It is algebra intensive, but by design, right? I mean, by design, it's supposed to be algebra instead of calculus. So yeah, you got that. Also realize we did really kind of nice functions. I mean, think about this one. This step function was off, on, off. That's it. And it was just a function 1. It wasn't even anything kind of crazy. So even with simple functions, with simple piecewise functions, these can get pretty brutal. And just so you know, what I'm looking for when you do these is primarily the setup. Like, can you find the way to represent that piecewise function in terms of the step function? Can you take the Laplace transforms and can you go backwards? And the backwards isn't so much the plug in the t minus 5s, although that matters. It's more, can you figure out what the form is that gives you the function? Now this one got a little bit more complicated, excuse me, because we had a sine and a cosine. So it led to a lot of stuff in there. But this is the general process. All right. So I think we're going to stop here, call this a day, because I'm sure most of you have already tuned out, and that's all right.
Not to watch the beauty happen.
So, but it was funny. I was playing catch with my son just earlier today, and because he just got done taking differential equations, and I was telling him where we are, and I was like, oh yeah, Laplace transforms. And he's like, oh my God, that's so cool. And I went, you are absolutely my son. Because most people don't find this cool, but I think he really appreciated the fact that it turned it, all of a sudden you're not doing calculus anymore. So he clearly thinks like a mathematician. He claims he wants to be a physicist. We'll see. We'll see if he can come over to the dark side. But I do. I find this really cool. It's amazing in its, I was about to say in its simplicity. I know it doesn't feel simple, but it actually really is. Like you think about what we're doing, it's just
All right, let's just do e to the minus st times this thing. And then it turns it into algebra. I mean, it's a really simple first step to get you out of calculus world. And I really appreciate, especially back in the day, that when calculus was new and difficult, this definitely made things easier for them. Anyway, okay, so that's really all I want to show you about Laplace transforms. So what we'll do Wednesday, we'll start into higher orders. What do we do when we have a third derivative or a fourth derivative or a fifth derivative? Spoiler alert, nothing different. Nothing's going to change. We're going to do the exact same kind of things that we've done. We're going to have to talk about how we augment a few of the steps that we've done. But in general, it's going to be the same kind of approach. All right. The last thing I wanted to add about exams, some of you have gotten your exam scores back, some haven't, because I was in the middle of doing it, didn't get quite finished. If yours hasn't been graded yet, it will happen in the very near future. So look for that sometime soon. All right, so I'm going to go ahead and stop recording for today.